and you will tell me if you can see the things we'd hope to be seeing. Can you see the title slide?
Yep, looks good on my end.
Cool. Let me just quickly sort of move you all out of the way. Okay. Oh, thank you, Nathan. Thank you so much. Thanks for inviting me to be here. Thanks for kind of reunioning me with a bunch of folks who I see on this call. I think actually maybe all the members, the living members of my PhD committee are actually here, which is kind of really wonderful to see you all again. Plus many folks from my former life in Hawaii. So it's really lovely to be here. And thank you all for coming. So I can't totally see people. So if you have questions in the middle, do whatever you need to do. I'm happy to answer if I can. Nathan says he can kind of monitor who is asking questions, but if all else fails, I'll hope to leave time at the end. So hopefully everyone knows I'm going to talk today about the 2025 Tracy Arm landslide and tsunami. I'm going to be focusing on the part of this story that I've been working on, which is precursory seismicity. There are earthquakes that we think are associated with preliminary slip. And so the authors that you see on this first page are people who have been working on that part of the story with me. But one of the really cool things about this project is that it's been so collaborative and so kind of broad reaching. So some of you may have seen we had a paper that just came out in Science a couple weeks ago. It'll be in the actual kind of the physical paper version of the journal in June. But as you can see, it's a long list of characters who've been involved, and we've got climate scientists and glaciologists and seismologists and tsunami scientists. And so really everybody on this list is the appropriate co-author to this talk. But maybe kind of, if we're talking about the people who have done work on this, I've got to start off with introducing you to the motor vessel David B. And just by way of explanation, I'm going to give this talk kind of from two perspectives. I'm going to tell it as I learned about it and as I became involved in it. And then I'll kind of tell that narrative first, and then we'll jump back into a little more of the science and the precursory seismicity. But this boat here, it's a 65-foot vessel built in 1929. It was originally a towboat used to bring rowboats out to the fishing grounds in Bristol Bay, Alaska. And about 30 years ago, it was purchased by a couple by the name of Jeffrey and Christine Smith. You're going to hear their names a number of times in this talk. And they run it as kind of a floating bed and breakfast. They can take up to 8 passengers, and they spend the summers in the Inside Passage in Alaska, taking people in and out of Juneau and Petersburg and Ketchikan. Jeffrey and Christine also happen to be my neighbors. They live just a few blocks down from me in Bellingham, Washington. I actually met them by buying their friendship by taking a cruise 20 years ago. So we've been good friends for 20 years and have always really enjoyed kind of swapping stories of their perspectives on Alaska and, of course, my more geological interest in things. So when this story starts, Christine and Jeffrey were leading a tour in southeastern Alaska, and Christine is the chef on the boat as well as the primary naturalist. Both of them are ship's captains, but Christine gets up very early in the morning to make breakfast for the passengers, and she keeps a journal. And on August 10, this is what she wrote in her journal that morning at 04:09 local time. Happy to be tucked away here at Ford's Terror. It's calm but raining and foggy. At midway, it's blowing 25. Should rain all day. The waterfalls will be beautiful at sunrise. And this is a photo she took on that morning. You can see it was in fact quite rainy, quite dreary. I'm going to call your attention to this sandbar over here. And by the way, I have to comment that I'm going to call your attention to is totally a Mike Garcia line that I stole from him about 20 years ago. So thank you, Mike. I use that all the time. You don't know if you know how often you give that in talks, but it helps. So here is the sandbar that's right here. We'll come back to that in a second. Let me tell you what she means when she says she's in Ford's Terror. So we've got a map of part of the Inside Passage over here on the left. I'm hoping you can see the mouse move. Maybe, Nathan, maybe you can just tell me if people can see that. I don't know how it works. Okay, thank you for all the thumbs up. All right, so the city of Juneau, is right here, and we're zoomed in kind of in this area that you see in the larger image. So Ford's Terror is a little inlet right here on this larger fjord called the Endicott Arm, which terminates at the Dawes Glacier. That's actually one of a pair of fjords that you enter in this area. So Harbor Island is at the mouth of this passage that goes for the Endicott Arm in the south and the Tracy Arm in the north, and the Tracy Arm terminates in South Sawyer Glacier. There's also Sawyer Glacier, or sometimes called North Sawyer, here at the top. So on this morning, Jeffrey and Christine were anchored here in the Endicott Arm. And you'll see that at the beginning of this, we all thought whatever was going on was probably in Endicott Arm for that reason. So this is Ford's Terror on a beautiful day, a little different from the day that Christine started that journal entry. This is the David B in the middle. And again, here's that sandbar that I mentioned. So on the morning of August 10, Christine got up early, as I said, to make breakfast. Jeffrey got up a little bit later, probably around 6:15 or so in the morning Alaska time. Jeffrey went outside on the deck and apparently called to Christine and asked her to come outside because he felt that what he was observing was unusual. Christine came out, and the two of them described to me a ton of water pouring over this sandbar. So they saw these surges of water coming in and out of Ford's Terror. And they watched this for a bit. They knew this was anomalous. And the first thing they did was to go online. They had got Starlink last year, so they're able to go online. And they went online to look at the USGS earthquake webpage and the Alaska Earthquake Center's webpage to see if an earthquake had occurred nearby that might have generated a tsunami. So they knew to do this. They saw there was no earthquake that had occurred in this area. So the next thing they did was kind of hypothesize maybe this was a collapse of Dawes Glacier at the far end of the Endicott Arm. So they were really puzzled about what might happen. And so Jeffrey turned to Christine and said, well, I guess we messaged Jackie. So again, we've been friends for 20 years. They often refer to me as their pocket seismologist because they can pull me out and ask a question. I'm assuming that's the reason, not my size, but that they can talk to me whenever they've got a question about seismology. So sure enough, at 6:34 in the morning, Alaska time, 1 hour later here in Washington, they send this text. Good morning, Christine says. Jeffrey and I are anchored in Ford's Terror. There's a crazy surge here that's causing the water to rise by 2 to 3 feet on a falling tide. And again, they later, if you see this comment, they later amended that to be closer to 5 to 10 feet when they did kind of a closer evaluation of how the vessel was moving. Is there any seismic data, she goes on to ask, from Endicott Arm that would indicate a landslide somewhere? So they had already ruled out earthquake. They knew, because they've worked in this area for a long time, they knew some of the consequences of steep fjord walls. And so they sent this to me. I was just getting up, 7:30 in the morning local time, got my coffee and responded, whoa, I'll look and see what I can find. Stay safe. So you'll see all the times are 1 hour apart because of the time difference. I don't know this area terribly well. It took me a little while to dig into seismic data to try to figure out where the nearest station was. And when I did, the station I found is about 70 kilometers from Jeffrey and Christine. You're looking at 24 hours of data on a station located, like I said, about 70 kilometers away near Admiralty Island. And that's a kind of junky seismic signal, right? There's like nothing really super pretty there, a lot of low frequency noise. But this one thing of interest is this kind of spiky thing somewhere around 5:30 Alaska time. And if I zoom in on that, that's a plausible landslide, earthquakey signal, kind of not something that I knew immediately how to interpret, but it was certainly a reasonable time for what they were describing and an interesting signal. So I wrote back, there's definitely something happened at 1328 UTC. Can't find much data, but landslide seems reasonable. I'll keep looking. And then I can't get a location, but I'll see what I can get from the Alaska Earthquake Center and just checked again to make sure that they were safe. So looked around some more, couldn't find, there are not very many seismic stations in this area. So I said, I can only find data from 2 stations so far. The event shows up first on the one closest to you. So location near you seems plausible. So Christine, always excited about science. I'm so curious if it's land, glacier, or other. So again, here we are, 7 o'clock in the morning or so, 8 o'clock my time, and I said, well, I just wrote to a friend who does landslide science with USGS, and hopefully she's awake. So I wrote to Kate Allstat, some of you may know, in Golden. Unfortunately, it was a Sunday, and Kate was not, as a federal employee, couldn't work out of home, so didn't have a work computer. But I did contact her. While I was waiting for her to answer, I went ahead and looked at the data a little more. And so the first thing I did was filter out some of that junky low frequency noise. And what pops out is this. So now looking at about 4 or so hours of data. So we're zooming in on that larger spiky signal. Again, we're in Alaska time here. And now what we see is actually a little more intriguing. So you'll see that, if there are those out there who don't look at seismograms a lot, you're just looking at an indication of how the ground shook. This is a vertical channel, so how the ground is shaking up and down. And over the course of these 4 hours, you see kind of shake, quiet, shake, quiet, shake, quiet, these little spikes of seismic energy. Sometime around 4 a.m., it goes from individual spikes to something that's near continuous shaking, just a constant ground rumble, very weak but prominent, and then this larger signal here. And I'm going to describe these like this. I'm going to say we have a precursory earthquake signal, and then we have a landslide. And I'll talk a little more about why I think that's what these things are. But I want to dive into a little more detail first. So we're going to look at this in spectrogram space. So again, I know not everybody on here is a seismologist. So what you're looking at here, again, something on the order of whatever that is, 5-10 hours of data. Zooming in, we see again those spiky signals, those little tiny pulses of seismic energy. And in the colored frame, you're looking at what frequencies of ground shaking you've got. So if you can imagine, this is sound. It's all below the range of human hearing, but the ideas are similar. You've got your low notes on the bottom, your high notes on the top, and the yellows are the louder ones. So we see in all these earthquakes, they all carry kind of fairly broadband energy, kind of classically earthquakey. They all have about the same frequencies, although some of that could have more to do with the site than the actual source. You can see that it goes in those frequency bands, it merges into this very continuous signal where we cease to be able to look at really discrete signals. That then goes to a time where there's a little tiny bit of quiet and then this very large phase that I think is a landslide. So I was so convinced it was a landslide that I wrote this to Jeffrey and Christine. Convinced it's a slide, it has a beautiful precursory signal. So this is not something that I think is commonly how we look at landslides. And this brings up maybe one of the most strange coincidental parts of the whole story, that the only geologist or geophysicist that Jeffrey and Christine knows happens to be a person who has studied precursory signatures in landslides for over 20 years. So this is something that I worked on when I was with the Alaska Volcano Observatory, and these are a bunch of the papers that exist on this topic. So the actual first paper that identified slip at the base of a slide that I can find in the literature was Weaver and Malone in 1979. And this was a glacial failure on Mount Baker volcano, actually right here outside of the town where I live now. There's a couple things that have to do with some landslides that I studied on a volcano in Alaska, but you can see precursory seismicity associated with large ice avalanches. And then we go later into things that were slides that are not ice. There's one here, despite the fact that it's in Greenland, this was not an ice failure. These ones here in Japan, definitely in rock. We know there were a host of other ones in South Central Alaska, Iceland, Costa Rica. We've now seen precursory events on a number of these slides. And they all have the same seismic sequence. We're going to come back to what that sequence is like later, but it was the thing that convinced me that this was, in fact, a landslide. So I pass it on to Jeffrey and Christine. The event I suspect is a slide seems to happen again around 5:35. Christine, sweet, Jeffrey is telling our guest about Lituya Bay. So Lituya Bay, I'm pretty confident this audience knows Lituya Bay in 1958 was the site of an earthquake-triggered landslide that produced the highest tsunami wave, I think, ever recorded. It's actually relatively close to where Jeffrey and Christine were in the grand scheme of Alaska geography. So There they sat getting sloshed around by a wave and delightedly telling their guests about the fact that there was this monstrous slide years and years ago. So the character of the discussion changed a little shortly thereafter. Christine wrote, "We just got a report that a group of kayak campers at the head of the bay at Harbor Island had a kayak swept away and a bunch of their camping gear lost." Now, again, we still think whatever's happening must be close to them at Endicott Arm. If this happened at Dawes Glacier, it's like 27 miles away. So, holy shit, I responded. I'm going to send this to Kate, again with USGS. This makes this a much more critical story for us to understand, because now we have a sense that this is big enough to actually cause potential harm to people. Kate, in the meantime, had been trying to reach out to people in Alaska. So I send her this, and she's able to get emergency management activated in Alaska. I then get this text. I guess our current landslide detection system is someone in a boat texts you, who texts me, who texts Esgy, who texts Mike, who calls the emergency manager. So at this stage, we did get people into action. Turned out the kayakers had already called for help to local vessels, and they had been rescued by another boat that was in the area. So they all did just fine. So a couple hours pass. I'm still poking around at data. Emergency managers are making sure that everyone's safe in the Tracy Arm, and I get this message from Jeffrey. So we're now about 5.5 hours after the original event. So I just took people ashore, including Christine. The water is still surging around. I let everyone off, pushed the boat, and this is now the skiff he's talking about that you see in the photo here. It was just the bow touched, walked away for 3 minutes, and the skiff was high and dry. Took 4 of us to push back in. So at this stage, we realize it's been 5.5 hours and the waves are still going. So this is increasingly, we're getting a sense that this is a bigger event than we really had identified early. That then again gets amplified a little while later when I was able to get this figure from Esgy Karasozan at the Alaska Earthquake Center, that she had located the event at this green dot right here. So just for reference, this top fjord, that's the Tracy Arm. This is Endicott, and this little spur right here is Ford's Terror, where the David B was anchored. So I told them the AEC location puts it near South Sawyer. It's a really big event. Yowza, says Christine. And then by way of explaining, it created the equivalent of a 5.3 earthquake. So this was really our first indication that this was a very, very large slide. And in fact, this is the seismogram seen around the world, as sort of any decent sized earthquake does. Those of you who enjoy looking at seismic phases can see them here. These are just the wiggles recorded around the world. One of the things that's really intriguing here, you can notice that after every seismogram, all the way out to at least kind of, halfway around the world, you see these sort of sinusoidal waves that are kind of in the coda of the primary seismic phases. And this is actually from a seiche. This is water sloshing within the fjord and basically pushing surface wave energy into the ground. And so we can see in this case, it rang for several hours, this seiche, this water sloshing. We know from Jeff and Christine, of course, that the water was sloshing for quite some time after that. So this is something that increasingly we're seeing in seismic data from these type of fjords. There's another number of other examples that I can give you if you're interested. So the Coast Guard got out there that night, and this was the first chance that we had to see what's going on. So the following morning, I wrote to Jeffrey and Christine, got photos last night. You can see evidence. That's what we're seeing in this photo here. This is a screen grab from a video. You can see evidence of a landslide that appears to have hit South Sawyer Glacier. I suspect the slide triggered failure of the glacier front, but it's an early interpretation. What you're looking here, again, this kind of slightly lighter colored rock is where the slide came down. Everything you see here that looks like rock, this portion is probably legitimately rock. Everything out here is rock-covered ice. This is all the front of the glacier that has destabilized. So later that day, the USGS got out there with a helicopter, and we have this photo. So maybe this might have been a couple days later, actually. We are looking down the face of the slide. We're at about 1 kilometer elevation here. This is quite a high slide area. Here is South Sawyer Glacier, still covered in a fair amount of rock debris. A lot of the ice here has cleared out. But I want to call your attention to the other side. And you can see here this area that is stripped free of any kind of vegetation. A lot of this area is heavily vegetated. But when the USGS flew over here, they were able to look at this clear-cut area and get an estimate of how high the vegetation was cleared off. That caused me to write to Jeffrey and Christine. Estimates are that the slosh on the other side of the fjord from the slide ran up about 1,500 feet. That's Lituya Bay 1958 territory. That's huge, huge, Christine responds with. And again, kind of like before, this was sort of a turn for us in kind of our sense of what this event was. You know, it started off pretty exciting, and this was really recognition that we were now involved in something that was substantially bigger. Christine's message to me, we've been really cognizant about how close to being there at that time we were. Our initial itinerary was to overnight there that night, but the tides were messing with our Ford's Terror skiff ride, so we switched around days. So Jeffrey and Christine have been running trips in this area for over 20 years. Excuse me. They run this trip a few times a year, going from Juneau into the Tracy Arm area. And every time they do it, on night 5 of their trip, they anchor in the Tracy Arm. And this was night 5. And it was solely the fact that the tides were wonky, that they stayed in Endicott and in the Ford's Terror for the first time in 20 years. And as Christine says, I've been seriously weirded out by how close to being pummeled we were. I think we used up one of our 9 lives. And it was the first time that I really started feeling emotional in a very different way that I'm used to with my science. I know some of you have likely had that experience as well. So Christine's comment that day, I would have slept a lot longer. I was tired from all the excitement of yesterday's landslide and tsunami. It's been one of my nightmares for as long as I can remember. So I'm going to switch over to some of the data that we received about this. So we're looking now here at satellite imagery that shows the progression of South Sawyer Glacier over the last 20, 30 years, or actually more. I'm older than I know. Okay, so 50 years. So you can see this photo, the satellite image, was taken on August 7th. The slide was on August 10th. You can see that in 1979 to 2000, the terminus of the glacier was kind of up here in this area, but then it began a very rapid retreat, 2005, 2010, 2015, all the way back to August 7th, and this image was taken that this was the front of the glacier. So we saw really, really rapid glacial retreat during this time. We're also pointing out here a few areas where we think there were minor rockfall. Between these images, a couple of them were actually close in time to the big slide, but for the most part, there was no indication whatsoever that this area was going to destabilize. The next image shows things as they were 3 days after the slide. So now you can see the area that cleared out. We know there's some extent of submarine landslide deposit. We see, and we're going to come back to this in a bit, the tsunami trim line that we'll look at all around this area. We can see this whole area was covered in rock from that. And I bring this up because over the course of those 50 years, the glacier did not simply retreat, it thinned. And both of those things have the potential to debuttress the sides of the fjord. Whether that was a primary trigger, whether that was a secondary event, whether there's any connection kind of remains to be seen, but it has the potential to be one of the things that instigated or at least promoted this failure. So really things are most spectacular when you look from the ground. So this is again USGS photos from the day or so after the slide. So here is the landslide failure zone. This is about, again, a vertical kilometer that this thing slid, South Sawyer Glacier, and as you can see, just tons and tons of ice in the water. If we then reverse this and look on the other side of the fjord, this is the area that we see has been stripped to an elevation of 481 meters. That is a really hard number to wrap your head around. It is really difficult to know how much that is. So in the Pacific Northwest, I describe it this way: it is 2.5 space needles high. It's really an exceptional height. From there, the tsunami turned and ran down the fjord. You can see the trim line. This is upwards of 100 to 150 meters and all along this area. You can see an island here in the middle of the fjord. This is Sawyer Island. Sawyer Island looks like this now. There's a tree, but largely totally devegetated. And I bring that up because a similar view, you can see the glacier in the background up here in the upper right. A similar view 3 years ago shows that it was fully vegetated. This is about 100 feet high. So clearly we know the wave in this point was really high. But we can also look at what we think that wave was like. One of my colleagues on this paper, Patrick Lynette of USC, has modeled this. And so this is a figure in our paper. You can see the slide come down and really wipe clean the sides. The imagery it's on includes the trim line, so you can see how it matches this. You can see the run-ups listed on the side. We're going to change views, come down through the fjord. We're still sloshing up there in the far end, areas where the water ran way up some little stream valleys. We're going to turn now and look here at North Sawyer Glacier. The wave will wrap around here. There's a shoal right here. You can probably see that from the behavior of the waves, and you can see them really sloshing back and forth. I bring that up because this area right here at the shoal is exactly where Jeffrey and Christine anchor every time the David B comes into this on day 5, as I said, of the trip. This is where they would have been anchored. So I sent this to Jeffrey and Christine, and I received this message: we would totally be dead. We watched it in slow playback speed. The place we normally anchor is 40 to 70 feet deep. The model goes from 150-foot wave to minus 30 as the wave goes over it. So this is a picture of the David B from previous years in exactly this area. So you see there's just super vertical walls. They often see mountain goats here. I know they were very worried about the fate of the mountain goats. So again, it's very hard to get any idea of how big 481 meters is. So again, Patrick Lynette made this video. I'm going to show this here. You might be able to hear kind of the rumbling in the background. That's I'm not totally sure what sound he used for this. I did send him actually some sounds from old Hugo data from those of you who knew me back in the 90s, knew Fred Denebier. This might be the actual sounds of a submarine landslide, but I'm not certain. So this is the view if you are on the water, because in this you are on a jet ski, my friends, and this is your attempt to escape the Tracy Arm tsunami. It is kind of Minecraft level graphics, but that's because this is a real model. This is not attempting to be pretty. This is attempting to be accurate. So I unfortunately know relatively little about the model. This is not my forte, but Pat Lynette is the person you want to talk to at SC. Here you are going 70 miles an hour, I believe. Luckily, jet skis are buoyant. So we're going to come back up to the top. So I think this is a really excellent way to tell the public what these things are like. A little bit better than just saying 481 meters. This is actually being turned into a video game when you can try to outrun the tsunami. It's going to be made freely available on one of these streaming services. Okay. Other ways we try to explain this. This is a slightly modified graphic from one that Stephen Hicks made, my colleague, in that you can pick your sort of tourist attraction of choice. I added the Space Needle here again from my colleagues in the Pacific Northwest. But you can see a variety of large tsunamis here, Tracy Arm being second only to Lituya Bay. So you can see that it would have covered the vast majority of the large tourist attractions in this world. So it is entirely possible that events like these may become more common. So this is something that's looking at 27 tsunamis that have hit higher than 50 meters over the past century. And these are all things that have occurred with, all of these have occurred due to landslides. I believe this is not my figure. This is my colleague Christian Svenevik in a paper that he's still working on. But the point being that a huge number of these tsunamis have been cryogenic. That is to say, they were triggered by ice failures or failures in permafrosted areas. And we bring this up because it's entirely possible that in times of climate change, events like this may become more frequent. So it's a hazard that may be amplified by the impacts of glacial retreat and glacial thinning. So why is this a huge hazard for us? Well, we've seen this image before. This is the Google Earth image of this area. I'm going to zoom in now, though, on this area here at North Sawyer Glacier. So this is a pretty random Google Earth image. I just grabbed this. It's probably taken maybe 3-5 years ago. So again, North Sawyer, or actually just called Sawyer Glacier. And I grabbed this because right here in the front, you see that this particular image captured a boat sitting in front of the glacier. This is a very, very heavily trafficked tourist destination. You can also see this is before the slide because there's vegetation all the way to the waterline. The boat you see here is the Zaandam, which is a cruise vessel that carries 1,400 passengers, 600 crew. So you can imagine, had that wave come through at a time when a cruise vessel was there, 2,000 lives would have been at risk. On any given day in the Tracy Arm during the summer, there are anywhere from 5 to 25 vessels. These are only the ones that subscribe to the AIS system. This does not include kayakers. This does not include many personal sailboats and whatnot. So the number is likely higher. Any given day, there are dozens of boats that venture into the Tracy and Endicott Arms. At the time of this landslide, it was 5:30 in the morning. There was only one boat in the Tracy Arm at the time. It was near the mouth, and it was after a large S-turn, which broke up a lot of that tsunami energy. They experienced some pretty strong currents, but they had no idea that they were experiencing a tsunami. So the timing of this was really sort of nothing short of miraculous. So the big question we've got is, will we know when the next landslide is coming? And landslides are notoriously difficult to anticipate. We didn't see any indication in satellite data that there were fractures opening up, that there was precursory motion, that there was any kind of deformation, no indication that something was likely to happen. But my hope is that we have signals like this, and that maybe if we can learn more about what these are, they could be a clue to helping us. So I'm going to spend the next 10 or 15 minutes just talking about these precursory seismic signals. Again, precursory discrete earthquakes, continuous ground shaking in the form of a tremor-like signal, and then the slide itself. So we've now identified these before at least 20 landslides in at least 8 locations. You're seeing those locations here. One is misspelled. Oops, sorry, that's Askia. There's extra A in there. Sorry about that. Most of these signals are the same pattern: discrete quakes, tremor, failure, virtually every time. I think these are not widely known for at least one reason that I blame myself for. The very first several 3, 4, 5 papers that were written on this topic were all about observations of glacial failure, all ice avalanches and ice slides. And when I wrote about these back in 2005, 2007, I thought we had this unusual sequence because of ice. I thought it was a unique characteristic of the rheology of ice that allowed it to stick slip for a long time before breaking apart. And so like my papers are in the Journal of Glaciology, right? I don't think anybody who studies landslides necessarily ever saw those. So we were kind of misled by me. I'm wrong. So that was, a little confusing, but it actually turns out that these things do happen a lot in ice. And so I'm going to tell you a little story about a volcano called Iliamna in Alaska. So this is a photo of Iliamna, spectacular volcano, heavily glaciated, as you can see. But it has these recurrent glacial failures. So you can see here in this photo, there's been a large avalanche where it's removed a thick layer of ice from the volcano. You can see that it's picked up some rock and trained it here as it moves further down. It has these things every few years. And if we kind of zoom into the top, we can see that these really represent a slab failure, a slab of ice sliding on the ice-rock interface. They couple very well into the ground, so we see these really clear stick-slip earthquakes. Almost all of these Iliamna events exhibit this precursory seismic signal. So this is a place where we can really look at these in detail to try to understand why they behave this way. And so you're looking here at 10 of them from 1994 down to 2019. There have been others since. This is, I I would say it's a random selection. It's not. You all know in your random selections, you pick the prettiest ones, but here's what they are. Time scales are all different on them, but you can probably see they all start with little precursory quakes. You can see them, whoops, sorry, I kind of went backwards there. You can see them all kind of stuttering along and then turning into this continuous tremor. You can see these two are virtually identical, despite in the same year, they actually occurred on different sides of the volcano. All right. Here's another one, 2004, a lot of them that year, 2013. All of these things have pretty much the same sequence. And I'm described some of the characteristics of these sequences. First, those discrete earthquakes. They're all what we call multiplets. They all look the same in time series. So this is an example of those discrete precursors on Iliamna in 2014. You can see that each one of these is a separate earthquake, and they all look really, really similar. That tells us that it's the same source process, and it's occurring in the same location. So something is slipping again and again and again. In fact, sometimes there are multiple such clusters, multiple multiplets, in a single slide. So here's data from Iliamna in 1997. These white waveforms, these are stacks of multiple similar looking events in the precursory sequence. The tartan here is an indication of similarity. So this big square, this is somewhere in the order of probably 50 or so earthquakes, same event along the vertical, horizontal and vertical axes compared to one another. So what this means is all these 50 to 70 events look the same. There was also a sequence of about 30 that all look the same, but slightly different. Here's one with maybe 20 that all look the same, but slightly different. So we've got these multiple areas that are all acting in this precursory period. But they're not going from one type to another, at least in this circumstance. Colors are kind of muted here, and I apologize for that. But this is that sequence. The red dots are all earthquakes in one of the clusters. The blue dots are all earthquakes in another one of the clusters. The green are in another cluster. So we can see basically there are multiple places on the base of this slide slipping simultaneously on and off. Some of these clusters stop, some of these start up later, some of them go the whole time. This was really clear at Tracy. So what you're looking at here, I'm going to start with the panel on the right. These are clusters, these are multiplets. Kind of all the events in gray, they're very small, they're kind of lost in noise, but when we add them together, the signal amplifies in black. So here we have 224 earthquakes that all look the same. This is a cluster of 94 earthquakes that all look the same. 86, 56 clusters of events in the precursory signal before the Tracy Arm landslide. These panels over here on the left tell us when all those events happened in the 5 days prior to the slide. These are ranked in order of size, not time, but I'll walk us through in time. You can see that starting about 5 days before the slide, cluster number 5 that has 56 earthquakes in it was stuttering. Quake, 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 several quakes a day. They became more and more and more frequent, then extremely frequent. This is the number of events happening every hour. And then they stopped. Right around the time they stopped, cluster 2, cluster 7, clusters 8 and 9 initiated, which tells us other spots on the base of the landslide began to fail. When those stop, we get a couple other clusters here, number 13, number 12, 3, and 1. All of these occurring at slightly different times. So there's some kind of stress transfer to some other place on the slide that is failing. Right now, we don't have good locations on these. There were very few seismometers in the area. So trying to figure out what that process is going to take a little bit of black magic. I'm hopeful we can do something with it, though. That cluster that showed a change in inter-event time actually mimics some of the other ones we've seen. So here's an example of the precursory sequence in the Carrot Fjord, Nuugaatsiaq, Greenland in 2017. Just a spectacular example of inter-event timing in the precursory sequence. It becomes more and more and more frequent before the landslide itself. This, by the way, is the tsunami, this long period signal here detected on that seismometer. If we plot the inter-event times, you can see there is really just a linear path to failure. If we see things like that, maybe we would have the potential to say, not only do we think there's a slide, but when will it happen? The problem is they don't all do that. Here's one of the Iliamna ones, 2004. It's a pretty random occurrence. So maybe that tells us something different about process. In fact, at Tracy, we had both. Here is that very long one that lasted days. You can see it progressing toward failure. Again, this is inter-event time in seconds on the vertical with time where the red line is the failure. On the other hand, these kind of blue ones, they just kind of pop off randomly. This red one, no progression toward failure. So there are stories within here that still have to be told. We can look at magnitude as a function of time. So this is work by Seven John, who is was a graduate student until like 2 weeks ago, defended his thesis. And he's been working on the Tracy Arm cluster as well. And you can see that the events get larger as we approach failure and then smaller. I'm going to put a little caveat on there. These become so frequent in time that they overlap. And I think at that point, there's so much interference, it's very difficult to know the total, the true magnitude of these events. Overall, seismic energy does decrease toward the end, which is another thing we don't yet really understand. Maybe one of the most important things that we need to know, though, is this. This is the duration of the signal, the precursors. And I say this because there's a question about could we use these in any really functional capacity. So you're looking here at hours before failure and the cumulative number of precursory events. So over here, you can barely see the two Iliamna slides I've put in here. I should point out the number of precursors here, I think these are scaled differently. I think these two have a different y-axis that looks like I cut off. These have fewer events. But you can see that there's almost nothing until 2 hours before failure, and then it skyrockets. In contrast, Tracy really began growing over days. If we have days to identify that this could happen, that's a very different process than if we have, or a different circumstance for us than if we only have a couple of hours. Okay. But maybe the biggest problem is that not all slides have precursors, and it is not entirely clear as to why. So this is an example of a slide on Mount Baker volcano here in Washington State. Beautiful kind of, surface that's been exposed after the failure of partially glacial ice and partially rock. Here is a very reasonably proximal seismic signal, 10 kilometers, nothing beforehand. That's a small slide. Here's Mount Meager, monstrous slide in BC about 15, 16 years ago. This is a pretty distant seismometer. We're 70 kilometers away, but there is just nothing visible. So maybe there were precursors we couldn't detect. And that's kind of the problem. We know everything on the left here had precursors. We've not seen them in all these ones on the right. But that doesn't tell us if there are no precursors or just no proximal seismic data. So of course, every seismologist will tell you the solution is to put out more instrumentation. I will say the same thing. I think that's what we have to know to see if under what conditions do we get precursors, and what does that tell us? What are those sequences like? So, in summary, we know that the Tracy Arm landslide, as I said, generated the second largest tsunami run-up ever recorded, potentially associated with glacial retreat and debuttressing, in which case this could be a more common phenomenon. We see these precursory sequences that have very characteristic behavior that vary in duration. We now know are not unique to ice, occur in a variety of lithologies, but we don't yet know really how common these things are. I'm going to leave you with this video. This was taken during a survey of the area just a couple weeks afterwards, partly just to show the extraordinary beauty of this area. This is Sawyer Island, devegetated following the landslide. You can see the glacier in the background, and you can see the trim line. So really this extraordinary beauty in a very peaceful perspective on Tracy Arm following what must have been a very, very violent day in August. So with that, I would be super happy to take questions. I will stop this. I will stop sharing it. I can figure out how to do that. I don't want to stop presenting. There we go. Neil Fraser. Hi, Neil. You just showed up on my screen. I can only see like 1 or 2 people at a time, but I'm so happy to see you. This is your turf. This is totally your turf here. But you're muted, so if you're saying anything, I can't hear you.
So just for folks who are from outside of NOAA, if you want to ask a question, there's a raise hand button at the bottom of the screen. You can get my attention with that. Gerard has his hand up. Go ahead, Gerard.
Yeah, I just told you we have this paper about humongous landslides in Hawaii, and we're desperately looking for a climate trigger, which we think we've found. We get a hint of it, but this is a long-term trigger, over tens of thousands of years. But whenever I give a talk about tsunami safety, and most recently one I gave in Ever Beach a couple of weeks ago, where I didn't mention this subject at all, I get this forest of questions about these massive landslides, and would we have any good short-term warning? And I thought about it, knowing a little bit about your work, and I said, yeah, we probably would. Now, I don't expect anything anytime soon. If we're right about the climate signal, then we don't expect one for another 15, 20,000 years. But I said that you're not going to get a gigantic landslide just happen spontaneously, especially since it's involving failure of rock.
Right.
And so you're going to see this thing creaking and groaning before it lets go, and those are going to be earthquakes. And so I said, I think that, and this is what I tell emergency managers too, I said, I think we're going to see hundreds of earthquakes before one of these things lets go. And of course, then the question is, well, what's the time scale?
Right.
And I said days to weeks, if we're lucky, months. Am I in the right ballpark?
I hope. So I have a student right now, the master's student, who is kind of trying to do a comprehensive analysis of what we know about these precursors, so we can start looking at how long are they? What do they scale with? Does the size of the slide give us any indication? Does the lithology give us any indication? What might other triggers have been? We've not really done, I mean, I'll be honest, when I looked at things at Iliamna and Mount Stellar and New Gatsiak and all these ones, I kind of looked at the hours beforehand. I really have not done a comprehensive search days beforehand. So since then, I've looked for some. It can be very challenging, particularly like at Iliamna, the seismic network is often pretty junky. And so knowing whether these are just glacial cracks, whether these are genuine volcanic earthquakes, or whether these are slip on the base requires locations and the fundamental number of stations that work. I don't always have that. So that's one of the outstanding questions, is how common is it to have a prolonged sequence? And I have to say that I don't yet know the answer to that question. Sorry, that's not going to help you in your next couple of talks. I hope to know better.
Thank you.
Hey, Neil has his hand up. Go ahead. You're muted, Neil.
Can you hear me now?
Yes.
Jackie, I really like this wonderful talk. Fantastic. I like this notion of debuttressing, and it seems to me, this will be obvious to you, of course, that, looking at the retreats of these tidewater glaciers in various places, you can use the rate of retreat and the local geology. For example, if it's, massive granite, you might not have that slope failure.
Mm-hmm.
So a prediction analysis could be done, and you could give a hazard rating to all those things, seems to me. You're probably already thought of that
No, I
long
think that's
ago.
a really good point. And I think what it does do is lets us know that we might want to do some better, not me, not a geologist, we need geologists to do some better mapping in areas where we do see potential debuttressing. And I'll say that at Tracy, again, going back, we didn't see any indication it was about to happen. But there are most definitely pre-existing structures in this rock that were likely zones of weakness. So,
Yeah.
now we can look and say, oh, these are places we might want to be really cautious about. But, decades and decades and decades, hundreds of years, those weaknesses existed and this thing did not fail. So again, that's why I suggest that the glacial debuttressing, if it played a role, may have just been,
Yeah.
one of many.
Yeah, the rate of retreat of that glacier, you just look at the things, that's really shocking. One more thing before I leave you. Pauline and I, in around 1995, went to the head of Tracy Arm in a 15-foot skiff.
I am glad that this was not the day.
But it was so damn cold, we didn't camp in Tracy Arm. We left.
I'm also glad of that. I'll just point out from that comment, there are 3 or 4 major cruise lines that have actually canceled all their trips to Tracy Arm this coming year. They're going to go to Endicott instead. I don't know that it's necessarily the case that Endicott is safer, but certainly certainly possible that the Tracy Arm slide may have actually kind of sideways unbuttressed, or weakened the areas next to them. So I can understand that. My friends Jeff and Christine are returning there. They are simply not going to camp in the Tracy Arm. They're not going to anchor there at night. So they will stay anchored somewhere a little wider.
You could make an argument that Tracy Arm is now safer.
You could, except you could also look at the lump next to it and say, oh, that makes me nervous too. So it is hard to know.
Anyway, thank you, Jackie.
Thank
Great.
you.
Okay, so we have a question from NTWC. Go ahead, Kurt.
Yeah, thank you very much. I'm certainly very interested in this as a new employee at the NTWC, but I understand this is a difficult problem. I think it's promising that there's these seismic signals that could be used to, predict would be fantastic, but even just detect a large landslide potentially generated tsunami. But I guess thinking about the feasibility in operations, can these signals locate with some accuracy the location of the landslide, and also do these signals occur when landslides aren't occurring? Is there slope creeps or you'll have to forgive me, I'm more a meteorologist. Are there other seismic events that can produce these signals that don't fuzz?
Those are really important questions. Yeah, I agree. So, let's start with whether there are other things that create these. Volcanoes have weird signals. It was not terribly surprising to see kind of stuttering and tremor in volcanoes, but those are typically something like this would be an erupting volcano. That would be a fairly obvious thing. I will tell you, I have seen exactly once on Iliamna a signal like this that didn't seem to have a slide, but I recorded it on one. There was only one functional instrument at the time, so I cannot be certain whether it was stuttering that didn't fail. That would be your false alarm situation. I think your point is a really good one about the value of simply detecting that it was a slide, even if we couldn't provide a warning about it. But to your point about could we locate with it, that really is going to depend on the size of the events and how many stations there are. Volcanoes are great for this because we have lots of seismic stations. Southeastern Alaska, not so much. There are very, very few seismic stations in this area. So we could, it took a lot of work on Esgy's part to get a location for that slide, and we really can do very little with the small precursory signals. So note that I'm assuming these are on the base of the slide, and I'm doing that based on Iliamna work. And Iliamna, I can locate them, and I can see that they locate near where the head walls of the slides are. Could not do that with Tracy. There are some examples. Esteban Chavez, who is a volcano seismologist in Costa Rica, has seen these precursors before several slides at Irazu volcano. Again, just a density of instruments. He doesn't see the precursors on instruments that are further than 100 meters from the slide. So in that case, you would literally just have to have an infinite number of seismometers on the planet to do this. So hopefully, we don't really know why they're large in some areas or not. There's a lot of work that has to go to know how well we could locate them.
Okay, yeah, so it sounds like more instrumentation would go a long way.
More instrumentation would go a long way, yeah.
I suppose for the very large events, so like I was playing around with some of the previous, or with the Tracy Arm data, and I thought I was able to triangulate a location using long frequency, but this is one of those, it's not my field, I don't want to, like I...
Let's talk and you can show me what you've done, because I'd be excited to see.
Okay.
Yeah.
It would, yeah, I'd certainly like to talk with you more. So yeah, I'll let the next person ask their question.
All right, Scott's next.
Hi, Jackie. As usual, that was fantastic. It's always bothered me a little bit that these things are called, these big Alaskan sloshes are called tsunami, especially when people show graphs or figures such as yours that have Tracy Arm and Tracy Arm next to Tohoku. And and the heights are just crazy. And I guess I'm wondering, might there be a native Alaskan word for these things that we could use instead? Just because, it gives people I think, a false idea that you can get ocean basin-wide tsunami that are as high as Lituya Arm was or Tracy Arm was.
I think that's a great point. I showed a figure, I'm not going to bother sharing my screen again, but I showed the figure with sort of the Eiffel Tower and the original version of that my colleague made, I won't throw him under the bus, showed like breaking waves going up there. And I actually pulled it into Illustrator and modified it to look more like slosh, like running up, because of exactly that point. You know as well as anyone, tsunami is the word for harbor wave, right? It's the wave that fills the harbor to distinguish it from that sort of short period peaky thing. So in that respect, yes, this is consistent with the description of a tsunami, but you're absolutely right that it brings in these huge misconceptions of what this is. I don't know if there's another word. I would love us to be able to describe these in different language, because there's so much misunderstanding around these things. I do feel like, and this is an audience that I should not even open my mouth around, because this is an audience that knows this much better than I. But simply, since 2004, having video of tsunamis has certainly transformed how I teach about them, because I can finally show, like, no, this is a flood, right? And so the challenge is, how do we maintain that perspective and do this, whether it's terminology or not? I agree with you. I don't know if there's another name, and it's a worthy thing to look into.
Thank you.
All right, Mike, you're next.
Hi, Jackie. Thank you very much. That was a great talk.
Thank
What
you.
I wanted to ask you was whether or not you thought about this as an opportunity to elicit private support for doing science in this region. Might the tour companies be willing to fork over large sums of cash to support a network that would monitor this more closely?
Thank you for that great idea. So I love that. I will tell you that it's been really interesting talking with the cruise companies. I've only talked with a few. I've talked with all the vessels that were in the area at the time. At least one company that shall remain unnamed didn't really want to go on record. It was like a while before they were really and yeah, and I see the message, no worry that people have to jump off for another meeting. I realize that I've taken up all the time. So thank you all for being here regardless. So some of them are kind of not wanting to talk about it. But the other thing is that what I want to do, and what I'm writing in the middle of a proposal right now, if NSF ever funds anything again, I'm writing a proposal to go back to Iliamna, because that is a place that gets them every few years reliably. I feel really optimistic that if we could put a dense network out there, we'll catch one. We'll catch one of these slides, and we can locate them, and we can see if there's a progression, and we can look to see where the slip is happening and what its evolution is like, and whether there's deformation associated with the slip, what the climate is, the local climate. So I think there are good things that can be studied from this. the cruise companies are not going to fund me to go to a volcano to do it. But your point is a good one and maybe worth thinking about. So thank you, Mike.
Good luck, Jackie.
Thanks. I appreciate it. I'm glad to see you here.
Okay, we'll let Justin have the last question, and I think we're going to have to end it.
Yeah, totally.
Hi, thank you again for the great talk. I was wondering if there was any measure or estimate of soil on, or soil thickness on like Sawyer Island or anywhere around there. Were there any pockets of soil left over in those surveys?
Interesting question. So I don't totally know. There were a couple of surveys on Sawyer Island. There was a group that actually had a tide gauge out there. They went to try to retrieve it. It was torn away, metal ripped to smithereens. But I know that they did hike around and measure sort of where vegetation was left, and they saw there were like brackish water on the top of these, these blueberries there. So I think most things were stripped clean, but I know at least there was some vegetation. I don't totally know, but if you ping me, I can try to find that report and see what was there.
Okay, thank you so much.
Sure thing. Super nice to see you all. Thank you all so much for joining me on this. And again, just so nice to see all these familiar faces. Awesome.
Hey, thank you, Nathan, for setting this all up for us. Thank you much.
Thanks, Nathan. Bye, everybody.